This is Mission Laika, linear algebra in kinematics and aerodynamics. It's finally time for our journey to end. Having survived all the adventures during the flight, the last challenge is to land the aircraft safely. Let's look at the vehicle at the moment of contact with the ground. The landing is never perfectly smooth, and sometimes this can cause significant oscillations of the wings. Previously, we modeled oscillations as mass spring systems, where components of the plane, like the wing and the fuselage, were replaced by masses and connected by springs. Or we used the pendulum model. In this video, we will use a different technique. Since the airplane is a symmetric structure, we can reduce the problem and look at only one of its wings. So let's focus our attention on the right half of the plane. We will present the wing as a beam attached to the outside of the plane. This way we can focus on the relative oscillation, meaning that the fuselage stays fixed and the wings oscillate. The equation on the screen is a discretization of the beam equation. We're not going to focus on the derivation of this equation, just note that it models the displacement of the beam. If you remember the video on the simple mass spring systems, the equation might look familiar. However, here U is a vector of nodal displacement, containing deflections and rotations at different points along the beam. M is the mass matrix and K is the stiffness matrix. Both M and K are symmetric. The nature of the matrices M and K will be discussed in one of your future mechanics courses. Let's take a closer look at the nodal displacement vector U. Take, for example, a model with two nodes, the middle point and the end point. At each of these points there is a horizontal displacement U1 and U2, a vertical displacement V1 and V2, and rotations θ1 and θ2. So the total vector of nodal displacements will consist of 6 components. Let's look at the first equation in more detail. The first step in simplifying the equation is to multiply it with the inverse of the mass matrix from the left. Let's notate the multiple of M inverse and K as A. Now it's time to recap a couple of formulas. The definition of eigenvectors and eigenvalues is something that we will need to proceed with this model. Any non-zero vector satisfying the equation A times V equals lambda times V is called an eigenvector of the matrix A with corresponding eigenvalue lambda. We can assume that eigenvalues can be presented as a square of some value omega. Next, we will need the concept of a diagonalization. A is diagonalizable if we can express A in the form P times D times P inverse. To construct the matrix P, we set the eigenvectors as columns, and to construct the matrix D, we put the eigenvalues on the diagonal in the same order as the corresponding eigenvectors in the matrix P. But why can we present the lambdas as squares of some number? How do we know that they are positive? Well, for a start, M and K are symmetric matrices. They are equal to their own transpose. Then, also M's inverse is symmetric. You will check this yourself in the exercise part. However, the product of two symmetric matrices is not necessarily symmetric, which you can also see during the post-video exercise. There is an additional property that both M and K have. They are both positive definite. Unfortunately, this property goes beyond the scope of this course, but it is closely connected to the symmetry of the matrices. What does it mean practically? Well, M being positive definite means that for any non-zero vector x, we have that x transpose times M times x is a positive number. A 2x2 example of such a matrix would be this one. Computation of x transpose times M times x gives something that we call a quadratic form. From the graph, it is clear that this quantity is positive as long as x is not the zero vector. In our setting, both the mass matrix M and the stiffness matrix K are positive definite and symmetric. Well, then also M inverse is positive definite. Can you follow all the steps on the screen? Feel free to pause the video and check each step. Finally, the product of two positive definite symmetric matrices, M inverse and K, has strictly positive eigenvalues. That means that our approach of presenting eigenvalues of squares of some real numbers is totally valid. Now, to solve the system, we will use a technique called decoupling, which you have seen in the lecture about diagonalizations. For that, we will make a substitution y equals p inverse times u. If we multiply our equation of motion with p inverse from the left and simplify things with substituting the matrix A with its diagonalization, we will get the following equation. Here, D is a diagonal matrix. This means that the initial matrix equation has turned into a system of simple linear second-order differential equations, which you know how to solve. Solving this system allows you to determine whether the amplitude of the oscillations of the wings is dangerous for the aircraft. If you want to increase the precision of your calculations, you might consider taking more sample points on the wing. Of course, in this case, the matrices will drastically grow in size, and you might need some programming skills in order to solve that system. Try the exercise after this video to check if you can safely land the airplane. And congratulations on finally touching the ground after the long flight.